See here, this is core and this is cladding. These are the core and cladding are the parts of the fiber optic cable. Okay. Now in fiber optic cable, the light ray is propagating through the core material due to the refractive indices differences. When N1 is greater than N2, then this is incident and reflected. So the light ray, the information is in the form of light ray, is propagating through the core material by a mechanism called as total internal reflections. This mechanism is called as total internal reflections. Total internal reflections. Now this is the core and cladding or the fiber optic cable, but here the topic is inter-symbol interference. So what is inter-symbol interference? First we will see, and why this problem mainly occurs in optical fiber cable and wireless communication systems. Now see here, now the electrical signals, the output of the encoder is an electrical signals, the electrical pulses, rectangular pulses, binary 1 and binary 0. Now that electrical pulses are converted into the light. Let us take now I want to transmit a binary 1. This is binary 1 with a duration of TB, because each bit is having a duration of TB. So in other than the optical fiber cable, within this particular duration you can get the same bit binary 1. But what is this? Here these electrical pulses are transmitted in the form of light ray. Now the information is transmitted in the form of light. When the information is transmitted in the form of light, due to the propagation time delay of this particular light at the receiver, now this pulse gets spread. This is called as pulse is dispersed. Therefore this is pulse dispersion. Now why this pulse dispersion occurs? The pulse dispersion occurs due to the variations in the propagation times of the light ray. Why? Because this is only one single symbol. Now let us take, you can easily understand now. I just transmit a train of rectangular pulses. Now you tell me what happened. No, when I transmit a train of rectangular pulses, now this is one light, this is another light, one light, another light. Due to this propagation, due to the variations, this light will at t1 seconds, this is t2, t3, t4 like that, different times. Due to variations in the propagation times of the light rays, this pulse gets spreading. Now due to this pulse dispersion, what happened now? Now the first symbol, the first bit is spreading, the pulse is spreaded, and it will enter into the another bit. Now this pulse is spreading and enter into the another side, and this pulse is spreading is entering to the other side. Due to this pulse dispersion, one binary symbol causes interfere with the another binary symbol. One binary symbol is causes interfere with the another binary symbol. Actually this is the duration of TB, but it is extended up to here. This is the duration of TB, but it is extended to here. Now due to this pulse dispersion, one binary symbol causes interfere to the another binary symbol is called as inter-symbol interference. This effect is called as inter-symbol interference. Due to this propagation times of the light ray, due to the variations in this particular light ray timings, now these pulses get spreading, and this spreading pulse will overlap with another symbol and causes an effect is called as inter-symbol interference. Due to this intersymbol interference, the errors will occur. 1 will treat as 0, 0 will be treated as 1. Now, due to pulse dispersions, errors will occur, and this problem mainly occurs in optical fiber cable and wireless communication system. So, how to avoid this intersymbol interference? Now, to avoid this intersymbol interference, one solution is, one possible solution is transmit binary data in the form of raised cosine pulses instead of rectangular pulses. Means what? This is the rectangular pulse. Now this pulse spreaded one is called as raised cosine. So where we can see that, where it is available or not, we have to check. Now this spreaded pulse is called as raised cosine. Now this is the normal rectangular. Instead of this, you transmit in the form of information in the spreaded pulse itself, then the problem will not be occur. So instead of this rectangular pulses, you may use the raised cosine pulses such that the symbols will not overlap, intersymbol interference will not come in. Okay. So sir, what is raised cosine pulses? How it will be generated? Where it will be available? How can we get it? Then that we will see. Now first you note on this. Now you go back to your first class problems such that one solution is available at that particular point of view. What is that is, you just go through this. This is our basic problem what we have solved in the first class. This is a rectangular pulse of pulse width TB. This is the rectangular pulse of pulse width TB. Now whose Fourier transform? This is the Fourier transform. The rectangular pulse whose Fourier transform is nothing but a sinc function. Is it right or not? A rectangular pulse whose Fourier transform is nothing but a sinc function. This is 1 by TB, 2 by TB, 3 by TB, and so on. Minus 1 by TB, minus 2 by TB, minus 3 by TB, and so on. These are the Fourier transform of a rectangular pulses. The Fourier transform of the rectangular pulses is a sinc function, right? Now this is the sinc function in frequency domain. This is the sinc function in which domain? Frequency domain. Now you tell me, what is the meaning of raised cosine pulses? I want a raised cosine pulses means the pulse should be spreaded pulse in time domain. I want a time domain, but this is the same raised cosine pulse, but this is in which domain? Frequency. I want the same pulse in time domain. Now what is the meaning of that? If you want a same pulse in time domain means, can I say like this? Sinc function in time domain. Yes, the same sinc function, but I want in which domain? Time domain. This is none other than the sinc function in time domain. The sinc function in time domain is called as raised cosine pulse. raised cosine pulses. The sinc function in time domain is called as raised cosine pulse. Therefore, I want the same function in time domain. So, by apply the duality property, if you apply a duality property, now this is TB, 2TB, 3TB, 4TB and so on, minus TB, minus TB, minus 2TB, minus 3TB and so on. Now this is the raised cosine pulses in time domain, or a sinc function in time domain is called as raised cosine. Now what is its frequency domain? Now its frequency domain is nothing but, now this is capital X of t, now whose Fourier transform is nothing but small x of minus f. If it is even function, small x of minus f is small x of f. If it is odd function, small x of minus f equal to minus x of f. Therefore, this is nothing but now this is the Fourier transform of a raised cosine pulse. See here, this is the Fourier transform of a raised cosine pulse. Now what is the bandwidth of the raised cosine pulse? This is the bandwidth of the raised cosine pulse. Now the bandwidth of the raised cosine pulse is the bandwidth of raised cosine. The bandwidth of the raised cosine pulse, let us take represented by B naught, which is equal to RB by 2 minus 0. Therefore, this is the bandwidth of the raised cosine pulse, which is equal to B naught, which is RB by 2 hertz. This is the bandwidth of the raised cosine pulse, right? Now, this is the bandwidth of the raised cosine pulse. It is good, but this is which case? These are the sharp cutoff frequencies. Practically it is not possible. Therefore, this is the ideal case. This is the raised cosine pulse in frequency domain. It is ideal. This is the Fourier frequency raised cosine pulse in frequency domain for the ideal case. But it is not possible practically. Therefore, now for practically we should have some transitions, right? So now we'll see. For practically, this is the ideal case, B naught. Now, practical means some transition. Whenever there is some transition, which means, now this is the transition bandwidth, some excessive bandwidth. So practical filters will have such kind of transitions. Now see here, this excessive bandwidth is represented, this excessive bandwidth is represented by a factor. The excessive bandwidth is represented by a factor called as roll-off factor. This excessive bandwidth is represented by a factor called as roll-off factor alpha. Now see here, this is so 50% excessive bandwidth. So how much? This is ideal case. Now how much is excessive? 50%. Therefore, this is the practical case when excessive bandwidth of alpha which is equal to 0.5. This is the practical case. Right? But somebody is interested answer, no, I want a more practical case. If you want a more practical case, I can give one more example here. More practical case. Now these are the, now here the excessive bandwidth is 100%. So actually B naught, this is 2 B naught. This is B naught, 0.5 B naught extra added. Okay. Now here this is more practical case. This is the more practical case. So alpha which is equal to 1. Okay, 100% excessive bandwidth, 50% excessive bandwidth. So finally, by looking this, so can we find one method, one formula for the bandwidth? This is the bandwidth of raised cosine pulse. The bandwidth of the raised cosine pulse is RB by 2. This is RB by 2 into 1 plus alpha. Is it matching or not? Can you please check once? Now, this is ideal case. Ideal case means no excessive bandwidth. Now, in ideal case, alpha equal to 0. Now, see here. In ideal case, alpha equals 0. Substitute alpha equals 0. RB by 2. Yes, this is RB by 2. Now, or you may write like this, which is equal to B naught into 1 plus alpha. What is B naught? B naught is nothing but RB by 2. Now, if alpha equal to 0.5, if alpha equal to 0.5, 1 plus 0.5, 1.5 B naught. Now, what is the bandwidth? Now, yes, this is the bandwidth. If alpha equal to 0.5, the bandwidth which is equal to 1.5 B naught minus 0, which is equal to 1.5 B naught hertz. Yes, it is matching. Now, if alpha equal to 1, if alpha equal to 1, 1 plus 1, 2 B naught. Yes. Now, this is the bandwidth for 100% excessive bandwidth. The bandwidth which is equal to 2 B naught minus 0, which is equal to 2 B naught hertz. Clear or not? Matching or not? Okay. These are the, don't confuse about the raised cosine pulses. Raised cosine pulses is nothing but, the raised cosine pulse is nothing but sinc function in time domain is called as raised cosine pulses. So if you are transmitting the binary data in the spreaded form, so the symbols will not be overlapped. So within this particular time, it will be reproduced at the output side. That will not overlap. This intersymbol interference effect will be overcome. Okay, no. Now this is the bandwidth of rectangular pulse. Now the bandwidth of the rectangular pulse, which is equal to 1 by TB minus 0, which is equal to 1 by TB, which is equal to RB. This is the bandwidth of the rectangular pulses. Okay. Now you just see here. Now see here, this is more practical case and an excessive bandwidth of alpha equal to 1. So can you please check once, when alpha equal to 1, what is the bandwidth of raised cosine pulse? The bandwidth of raised cosine pulse, the bandwidth of the raised cosine pulse, which is equal to RB by 2 into 1 plus alpha is 1. So RB by 2 into 2 cancel, which is equal to RB. Then what you can understand? Now when alpha equal to 1, this is the important point. When alpha equal to 1, the bandwidth of raised cosine pulse, the bandwidth of the raised cosine pulse is how much? Which is equal to RB, which is same as that of bandwidth of, which is same as that of bandwidth of rectangular pulses. Rectangular pulse. Clear or not? And one more thing. Now this is alpha. When alpha equal to 0, when alpha equal to 0 means this is ideal case. When alpha equal to 0, the sinc function in time domain is called as raised cosine pulses. Am I right or not? No. Clear or not? Okay. This is the intersymbol interference. How to overcome this? Because see, you go back to all our PCM problems. So sometimes in PCM problems, he said that the binary data is represented in the form of rectangular pulses. If binary data is represented in the form of rectangular pulses, all answers will change. Because if it is a raised cosine pulses, now bandwidth is B naught, which is RB by 2, and excessive bandwidth is represented by a roll-off factor. Okay. Now one problem is solved here. Now this is the message signal, now which is sampled quantized and encoded. The message signal which is sampled, quantized and encoded. Now the message signal which is sampled and quantized and encoded, the output of the encoder is a binary data. But what is given is the binary data is represented in the form of raised cosine pulses. Now he said the ones and zeros are represented raised cosine pulses. Now he is not saying a rectangular pulses, he is saying raised cosine pulses. And a signal is band limited to, he is saying signal is band limited to 5 kHz. And the sampling rate is twice the Nyquist rate. First you find the Nyquist rate. The minimum sampling rate is called as Nyquist rate, which is equal to 10 kilo samples per second, and he is given sampling rate which is twice the Nyquist rate. The sampling rate which is equal to twice the Nyquist rate, which is equal to 2 into 10 kilo, which is equal to 20 kilo samples per second. The sampling rate is twice the Nyquist rate. The sampling rate which is equal to twice the Nyquist rate, 20 kilo samples per second. And what he is asking is, find the bandwidth of the PCM signal. This is the PCM signal. Find the bandwidth of the PCM signal for a different roll of factors, and he is given maximum quantization error is, and he is giving one more information, maximum quantization error. The maximum quantization error is 1% of peak signal amplitude. 1% of peak signal amplitude. He is giving this information. Now what is that? So you know that the maximum quantization error, which is 1% of peak signal amplitude, is AM. But you know that the dynamic range, which is equal to practically 2 AM, because dynamic range which is nothing but V peak to peak or V maximum. Now step size which is nothing but dynamic range by L, which is 2 AM by L, and the maximum quantization error which is equal to delta by 2, which is equal to 2 AM by L into 2, which is equal to AM by L. So the maximum quantization error which is equal to AM by L. This is the maximum. So can I equate these two quantization errors? Yes, if can equate these two quantization error, AM by 100, which is equal to AM by L. AM cancel. L equal to 100. You know that 2 power n, which is always greater than or equal to L. Therefore 2 power n, which is greater than or equal to 100. Therefore 2 power 6 is less than, so 2 power 7. Therefore n, which is nothing but 7. Therefore this is 7-bit AD converter. Now what he is asking is, he is asking now bitrate. First you find bitrate. What is the bitrate? RB, which is equal to 1 by TS into N, which is equal to 1 by sampling rate, which is 20 kilo into 7, which is equal to 140 kilo bits per second. Now he is asking, what is the bandwidth of raised cosine pulse? The bandwidth of the raised cosine pulse, which is RB by 2 into 1 plus alpha, and he is asking this bandwidth for a different values. Okay. Now this is the bandwidth. When alpha equal to 0, the bandwidth which is equal to RB by 2, right? So the bandwidth which is equal to RB by 2, 145 by 2, now which is nothing but 70 kilohertz. Now when alpha equal to 100%, so the bandwidth which is equal to RB by 2 into 1 plus alpha, So the bandwidth which is equal to RB by 2 into 1 plus 1. So therefore the bandwidth which is equal to 140 kilohertz, and alpha which is equal to 1.5, sorry, alpha which is equal to 0.5, 50% excessive bandwidth which is equal to RB by 2 into 1 plus alpha. Therefore bandwidth which is equal to RB by 2 into 1 plus 0.5. So the bandwidth which is equal to RB 70 kilo plus 35 kilo. Therefore the bandwidth which is equal to 105 kilohertz. So what we can understand, I am already saying that now when alpha equal to 1, the bandwidth of the raised cosine pulses, the bandwidth of the rectangular pulses are same. Now when alpha equal to 0, now this is ideal case. Okay. Now this is a more practical case. Now 50% excessive bandwidth